think we're recording. So as far as the final, like me having a lot of things to say at the very top, I don't feel like I have very much to say. That's different than the other review sessions. So I have very little planned for what I'm going to say. I have the equation sheet kind of queued up after this, but otherwise I was just going to leave it open to you guys to ask any questions or problems that you wanted to see. So I have at least the practice exams pulled up. I have Canvas ready to go so I could pull things up on my laptop and then solve them on the iPad, and then I am screen recording on the iPad. So this will be posted to Canvas. Hopefully it won't take like a million years to process and download and everything, and it will be up pretty quickly. But this will be on Canvas afterwards if you miss something. So what I do have to say is, I guess, I know I've shown my mental map of physics, but when I'm thinking about like the styles of problems in Physics 1, for the bulk of mechanics, I feel like it falls into mainly like 4 categories. So I would say like we have our kinematics and our motion stuff kind of on its own. Our forces and our Newton's second law, our dynamics stuff, all of that is kind of its own thing. Then all the work energy stuff is kind of its own stuff. And then momentum, conservation laws, that's kind of its own thing as well. And then we do have linear versions of all 4 of these things. We have rotational versions of all 4 of these things. And we've kind of outlined throughout the whole semester so far of like where these things intersect with each other as far as quantity goes. So acceleration is going to be blending, kinematics and forces together. Velocity shows up in all 4 of these things. Momentum, energy, kinematics, it can. And then more broadly thinking about like problems where the arrangement of our system is changing, and then thinking about what's being conserved at different points in time. When we're thinking about systems versus particles, kind of those are more broader, I would say, problem-solving skills and triaging that we do throughout the semester. And then other little things that I can always think of is like time mostly only comes up in kinematics, but it can come up in like momentum, so thinking about where certain variables are kind of showing up in certain places. Then kind of our special categories that stem from this is that we did get our fluids, which comes from then looking at forces in terms of pressures, looking at fluids in terms of the volume and the density instead of looking at things in terms of masses, because it just doesn't make as much sense for us to analyze fluids the same way that we analyze solids and other type of objects. We'll see in Physics 2 how we'll analyze gases and treat gases a little differently just because the type of matter is different. So we do have some special things that come out of forces, the fluids, and then mainly our new stuff, I would say, is like from restoring forces. Maybe what I would add here is just that pressure is force divided by area. But for our simple harmonic oscillators and for waves, those are consequences of restoring forces. So special type of forces in certain media, we can get these oscillatory phenomena kind of happening. And then the way that I would think about this question-wise, which I don't know how much I'm allowed to say, but that always kind of makes things interesting. I can say for sure there's 2 questions that are going to be on the new stuff. So the chapter 15, chapter 16, oscillations and waves. So we should have 2 questions on that. I would say to expect 1 question on fluids. And then the rest of the, I guess, 4-ish questions that would be left, kind of 4.5, because one of the setups you'll see will only be worth 10 points. The 6 other setups that you'll see will be worth 20 points. So 130 points available total on our final exam. So the last kind of 4 questions could be a little bit more basic in terms of like you're not seeing it exactly in terms of fluids, we're not seeing it exactly in terms of simple harmonic motion and waves. It's going to just be kind of everything else that we've done. So everything I would say from chapter 2 to chapter, when did we end on in rotation? I think it was chapter 11. So like leading up to all of that stuff. But yeah, the other thing I would maybe say, I don't want to step too far away from this. Oh yeah, that's right, I have a laser pointer on here. The other thing I would say is just to not, I guess maybe not forget that we still have some of the basics and some of the foundation stuff we learned that comes up in fluids. So yes, we have this, say, special equation for buoyant force, but we've still needed to use that in the context of Newton's second law. And that could then be related to something in kinematics, or it could be related to something in energy. So like those other things can still show up in fluids, but there would be, say, one setup that happens to be involving a fluid, and the 4 other setups wouldn't have that. Does that make sense? Hopefully that's clear. Any questions on that? So that's kind of really the only spiel that I have. Most of this stuff you have seen. A lot of this hasn't changed. Stuff on the first, second, third pages, that's all the same things that was on there from, and I guess even onto the 4th page from the first exam. What is going to be the new stuff is starting here with oscillations. So we do have the full position equation, the full velocity equation, just in terms of the displacement amplitude, xm, omega, time, and then the phase constant phi. We also have the equation for acceleration given at any time, and then the relationship for the acceleration at any time being equal to negative that omega squared of the position at any time. That's also on here. Some of the things that I guess aren't technically on here, but you could, like, you have enough that you can get this expression itself. One of the ones was from, so this would maybe be the easier one to get. It's just kind of ignoring the middleman on that second line, and then you can get the relationship between the way that we had it written in class was like the acceleration at any time divided by x at any time was equal to negative omega squared. So that's something you can get from those 2 things. The other one that people were asking for, but you can get, would be taking the velocity divided by the position at any time. So if we do take the velocity at any time divided by the position at any time, if I substitute in the equations for both of those, I get those xm's canceling, and then I could pull out basically that negative omega, and then I end up with a sine over cosine of the same thing. So the same thing's inside of the sine and inside of the cosine, and then we're taking that ratio, and then that simplifies to a tangent of everything that's inside of those 2 wave functions. So that's something also, if you need it, you technically have what you need to get there. I think the only other thing, which I won't erase this just yet, the only other thing I saw, I think, in emails was not explicitly having the relationship between the velocity amplitude and the displacement amplitude, and having like the acceleration amplitude versus the displacement amplitude. But now I am going to start erasing stuff. Only over here. But just to highlight the fact that like this is something that we went over in class a few times. I know in my class we did, that in general, anything you have that's out in front of your sine or cosine, and ignoring the positive or negative sign, but just whatever coefficient, magnitude of coefficient you have outside of your sine or cosine function in general is the amplitude. So it's not, to me, and to the other instructors, I'm going to serve as their mouthpiece. To me, it's not a gigantic stretch for you to be able to say, well, the omega times xm is what's in front of that sign for the velocity function, ignoring the fact that there's a negative sign there. So that's going to be my amplitude for my velocity. And then same thing for the acceleration, that you can pull out the omega squared times xm is everything that's in front of that cosine, ignoring the negative sign that's there, and that would be our amplitude. So just to be very clear on that and show you how you can get to those given what you have on the equation sheet, and part of why we're not including them. Questions on that or anything else on the equation sheet before this? Okay, then I think, so even though these are on other parts of the equation sheet as well, we have the relationship between the angular frequency, the period, and the just regular frequency. I never know what to call that. We have, let me erase some of these. We have the equation to get what the angular frequency is for a spring mass system. So we've got our omega square root k over m. On the top of the next page is where we have the stuff for the simple harmonic motion of, or the period first of the spring mass system, but then also if you were to have a simple pendulum, we have the period for a pendulum in terms of the length of that pendulum, and then g is the gravitational acceleration of whatever planet or moon or whatnot that the pendulum is sitting on. And then lastly, we have our wave section, which Professor Yates was very nice in putting the direction, the positive, negative x direction, as it corresponds to that positive or negative sign inside of the sine function. So the tops should match. So if this is positive inside of the sine function, then it's moving in the negative x direction, and then vice versa. If it's the negative sign inside of that sine function, then it's the positive x direction that the wave would be moving in. Same deal as far as identifying our ym here would be our amplitude, and then just being able to recognize everything else inside of this equation. I mean, the thing that keeps me up at night, if I'm being dramatic about it, is that this k, which is the wave number in this section, someone's going to take that to be a spring constant for something else. So just, I advocate for good bookkeeping and good accounting of things on your page, because I do, bless you, it can save you points that are significant. So just to keep that in mind. We do have the definition of wave number in terms of wavelength. Again, the angular frequency stuff is on there yet again. The different ways that we could define the wave speed for a sinusoidal wave, just kind of generally, and then for a wave on a string, the thing I would just, so this is something I maybe would have included, and maybe I should have caught this, but this is something that we can just give you if you need. The thing I would say for here, and maybe it's somewhere else on the equation sheet, someone can tell me if I'm wrong, is just to remember that that mu in the wave propagation of a stretched string, that's a tough one to say, is the mass of the string divided by the length of the string. And then otherwise, I would say that would be something we would give you if you needed it. Otherwise, I would say just knowing that this is tension. By the time you get to this part of physics, a lot of the times they'll start switching to using tau for tension, which we haven't used anywhere else. So that kind of comes a little bit out of nowhere, but conceptually knowing that that's going to be a force of tension on the string divided by the mass per length of the string itself. And then otherwise, the last thing that we have on here is just for if we have two waves moving with the same amplitude that end up interfering with one another and we get a resultant wave from that. Kind of same idea with knowing what the amplitude is by looking at the function. It would be everything inside of those brackets because that's everything outside of the sign.
So how would you use that?
I think there was like a homework question. I want to say there was a homework question where it was like, you know the amplitude of one of the waves that's making up this combined wave, and I think you know the phase constant, and they want to know the amplitude of the new wave. So if in a case like that, you only need to know, like, I think I called that ym prime in class. So we could call that whole amplitude of that combined wave, which we use y prime to describe its vertical component. Then the amplitude would just be everything out in front of that sign. So 2 times the amplitude of the wave that's making up this new wave times the cosine of the half of the phase difference between the 2 waves that are adding up to make this new wave. So I think that's just like a homework question of that's a little, can be plug and chuggy. Sometimes you have to just pull things out of a different equation before plugging it back in here. But I'd say in general, it's my professional opinion that the chapter 15 and 16 stuff can be a little plug and chuggy and more straightforward compared to some of the other topics. Yes, in the back? No, so we won't be looking at any waves interfering with one another that have different amplitudes. The only difference would be, a difference of a phase constant. That's a valid and good question to ask. But we're very confined in what types of interfering waves we're looking at. Other questions on equation sheet stuff? Yes?
So I noticed that the angular frequency for the pendulum isn't included.
No, but you have this relationship between period, angular frequency, and regular frequency. So if you know what the period is defined in terms of G and L, then you can technically get the other 2 if you needed them. All right, otherwise I guess I'm opening the floor to any and all questions. Yes?
In chapter 15, example 4, use subtractive like the calculated phase constant from pi. I just want to know conceptually why this goes to that phase constant.
Yeah, let me pull up chapter 15, example 4, so I have it in front of me. That was without the examples. There we go. Okay. And so we have at least some organization on here. Oops, I guess I don't want to do that. So this is chapter 15, lecture, example 4. So for this one, we were given at t equals 0. We know our x position is going to be negative 8.5 centimeters. So we can get that into meters. We know the velocity at that time is negative 0.92 meters per second, and we know the acceleration at that time is 47 meters per second squared. Okay, so for the first part, we were looking for the angular frequency. I think that part's a little straightforward. I'll at least just kind of write it out so that we have we know what we would have needed to do for that part. So for that part, I just took if I'm working from something on the equation sheet, I would be working from the acceleration at any time is equal to omega squared times the position at any time. And then I'm just changing my acceleration and position to be when time equals 0, because those are 2 values that I have. So then I could say a0 divided by negative x0 would be equal to omega squared, and then I could take the square root of those 2 things. Oh, I guess I also probably need my calculator next to me. Not at this particular moment, but that will be something I need. also have some candy. Not my full candy bucket, which I can go get if we need it, but I at least have some emergency reserves I was planning to add to the bucket today in case anyone needs sugar. Okay. So I don't remember what this number ends up being. I think that's neither here nor there, because our juicy question, our good question, is going to be about getting the phase constant, which is what we're interested in. But we need at least a way that we can get to that omega. I guess I will just write down an answer. And you could tell, I hope that this matches the solutions. I got 23.5 radians per second. Okay, thank you for confirming. Because then once we have that, if we want to know our phi, that's actually coming from that nice little expression that I derived, that I erased on the equation sheet, that looks something like this. So again, kind of at least maybe skipping 2 steps, but still pulling from things that we have on the equation sheet. Again, I'm just going to put in my velocity at time 0, my x at time 0, and then I have all of these things to be able to solve for phi, right? Because I know that my t is 0. Some of my givens are at a point on the page that we can't see. But this would be, or I'm putting in, negative 9.2, negative 0.085. So making sure we have that x position put into meters. Now we could put in this negative 23.5 radians per second. But then inside of the tangent, just since that t is going to be equal to 0, that whole omega t term is going to go away. So I'm just going to write that in terms of phi. So we can see that also pretty obviously, that just how that's isolated. So then if I simplify everything outside of the tangent, basically, I get a negative 0.461 is equal to my tan of phi, tan of the angle phi. And then if I do inverse tangent of that, ooh, and I actually think I had some nice figures that went along with this that maybe I'll pull up here in a second. Also, my calculator's in degrees right now, so I'm gonna report this in degrees. So I get basically like negative 25 degrees for my angle phi from this. But, and this is where I want to make sure I don't pull up the wrong thing. So this was solutions, and I did think that this was kind of give some context for people who haven't really thought about your sinusoidal functions in a while. And I think, okay, and then this is also, this would have been in radians. Now I'm just looking at the solutions that I actually had posted before. So like I do get back this angle phi when I do the inverse tangent, but if I'm looking back at this line here, where I'm evaluating the angle that I found for something else, then there's technically multiple solutions that would give me back this negative 0.46 part. So that's kind of what I start getting into on these solutions, is that basically for the tangent of x, if I take that x inside of my tangent and I add any integers of pi to that same number, I get back the same answer. But this angle phi that we're looking for in this part B, we're using that to plug into different cosine and different sine functions, and that's not going to give me back the same, like for the same value of x, that would give me the same tangent value. I'm not going to get the same cosine value for like that same angle. So part of what the pain in the ass thing is about looking for that phase constant is that we can get something out of this inverse tangent that completely satisfies that inverse tangent and is one solution of many, but there might be some other integer of pi away solution that will work for that tangent and work for our sine and for our cosine that's like fully describing this motion. So that's basically what you have to check. And it could have been that maybe, well, I guess it wouldn't have been that this one wouldn't have worked, because if I moved 2 pi, I'd still be inconsistent basically with what's going on. So then to jump back to, okay, so if I do my inverse tangent of phi, technically this is a solution, but then adding pi to that is also technically a solution that if I do, and I'll just kind of squeeze that in a different color, if I do tangent of 2.71, let me put my calculator back in radians, I get back negative 0.46. So that matches kind of following the math. This is already getting a little bit more mathematical than I like to go. But does that at least kind of start to answer? Because then basically what I'm doing, and again, I show this more so in this, so this is not as, I did not flesh this out as well in class, but I do have it in the solutions where now I need to know, like I'm solving for this amplitude of x, but I have these two different options for phi, is just to check if I do my one solution, that ends up giving me a negative amplitude. If I use that other solution for the angle, that ends up giving me a positive amplitude. And you could take this one step further and basically plug each of these values into the velocity function and the acceleration function and see which one will give you back the right sign of each of those values for like t equals 0. So I think there's like a few, there was like 1 or 2 homework questions with that same idea of like basically having to do that check of like there's more than one solution for what the angle could be, and we just want to go back and check each one and see if it matches the actual functions we have for position. Usually just position and velocity would be enough, because if both of those are right, the acceleration one will be right. So you really just have to pick the x and the v to check. Catherine?
So should the amplitude always be positive?
Yes, the amplitude should always be positive. So that was, well, I think I mentioned in class when I did do this the first time around, I didn't check the other solution because I was like, why would the physics problem be mean like that? But I got a negative amplitude, so then I was like, oh, so then it must not be this solution. It has to be the one, the next pi angle away from whatever this is to give me back the right tangent, cosine, and sine. Okay, but good question. I think that was a good place to start. Yeah?
And how do you know if it's the correct VM?
So if I wanted to check from here, basically then I would say, so my velocity equation would be looking something like this. What am I doing? Omega t plus phi. And I would just, did I do this? No, I didn't. Okay. I would just run this also with basically like do a case where phi is equal to the negative 0.43 radians and run the equation, and when t is equal to 0. And when phi is equal to the other radian number, and when you plug that into the sine with the xm, you would have had to find at least the magnitude of xm first. With the xm, with the omega, if you basically plug everything into the right side of that equation, you would expect to get back a negative 0.92, because that's what they told us at the very beginning. When t is equal to when t is 0, our velocity is equal to negative 0.92. What else do we want to see? Yes? Yes, I can. Is that good enough? Okay. All right. Does anyone have a question?
It's on one of the practice exams.
Okay. Do you know if it was the spring or the fall?
Oh,
So we had a fall 24 and a spring 24. I tried to separate it this way so that way I could do a better job of knowing which one is which. Which question on the spring? 5? Okay.
oh wait, yeah.
I'll convert the position. It's a block spring system. Okay. So we're looking, let me go back to, where's all my notes? So now we're looking at spring, practice final, number 5. So we were given the position of a block spring system is 0.2 cosine 8t plus pi over 4. X of t is in meters. And what they're not saying, but I'm going to safely assume, I think, is that time is in seconds. So that way we can assume that 8 in front of our time is going to be radians per second. Okay, so first we're looking for, if we know our spring constant is 128 newtons per meter, what then is going to be the mass of our block? So the first thing we have to connect our mass to our spring constant is going to be that angular velocity or angular frequency, depending on what you're calling it. By the time we get to this point of the class, both would be fine. So if I know my K and I could pull my omega out, so I can also just maybe do that anyway. I could pull out my amplitude is going to be that 0.02 meters in front of our cosine. Omega is going to be 8 radians per second, since 8 is what's in front of our t, and then our phase constant here is the pi over 4. That would also be in radians. So then I can square both sides and then get omega squared would be equal to k over m. And then if I want to get m by itself, I'm going to rebel against math now that I had to talk about math so much. And I'm going to draw an arrow indicating that I'm cross multiplying, but that the omega squared and the m are going to switch places. So I can get just spring constant divided by that omega. And I could put in the 128 divided by 8 squared, which I think should give me 2. And it does give me 2 kilograms. Okay, so that's a plug and chug part of our simple harmonic oscillator. For part B, we want to know the earliest time t greater than 0 at which the block is at its maximum position. So we do know the maximum position itself. Maybe I'll also just, well, I am going to post these, but if you need me to go back and look at anything, to take pictures or whatever you like, just let me know. So what I would do for this is basically just say, well, I want to know x is equal to xm. So I'm going to set xm equal to the rest of that equation I have, which I guess I can also say I know is equal to that 0.2 meters. So then I'm just going to take that 0.2 and I'm going to set it equal to everything else that I have to describe my x position in time. So my 0.2 will cancel out from both sides. That'll give me a 1 equals cosine of 8t plus pi over 4. if I take the inverse cosine of both sides, or if I just think about what angle inside of my cosine gives me a 1, that would be 0. But we can write out our inverse cosine of 1 is going to be equal to 8t plus our pi over 4, and then inverse cosine of 1 is 0. So now this will give us a chance to solve for our t, and this will be another place where there's multiple solutions, which is kind of hinted at in the way that this question is being asked. It's like very specifically saying the earliest time where t is greater than 0, so we want the smallest positive time that's going to fit our solution. And if I also divide this by 8, that would give me negative pi over 32 is equal to our time. And just to get a number for that, that would give me a negative 0.098 seconds. So again, this is a solution, this is a time where our simple harmonic oscillator will be at that maximum positive amplitude, but it's going to return to that same position a period after this time. So the next solution that I would say that like you can check that would be the one that's what they're actually looking for is the t that you found here plus the period, which we can get because we know omega. So I'm actually going to just start that on anew. So that would be, I don't know, maybe I'll call it t prime to give it something new. But then I would just put in maybe here the fact that my period is going to be 2 pi over omega, and I know what my omega is, so then I could put in that negative 0.098 plus 2 pi over 8 equals t prime. And if I take let's see, that's basically plus a pi over 4. That gives me 0.687 seconds. And then I would, for this, I'm not usually a work checker, but this is something where I would just go back and check my work, which again would just be plugging this in now to 0.2 cosine of 8 times this 0.687 plus pi over 4. And if I put that whole thing into my calculator, is that also going to give me back 0.2? And if it does, then that's my solution. And if it doesn't, I mess something up along the way. And well, not perfect rounding. I got 0.19966666666 repeating, but close enough. This is going to give me back 0.2, so I can check that that's going to be my solution is the time that you solve for plus 1 period. And that's definitely the toughest part, I think, of this problem 5. So we can take any questions on that before, if we need to. Maybe we don't. Okay. Then for our next parts, part C, I would say, is a little plug and chug, where we want to know now what the restoring force of the spring is going to be when the block is at the maximum position. So kind of the conceptual piece that we need to know is that the restoring force is the spring force. The magnitude of the spring force is K times the amount of stretcher compression, or the absolute value of that stretcher compression. So if I'm just looking when it's at that maximum amplitude, we have our K is 128. We have our amplitude is 0.2. and that gives me 25.6 newtons would be the amplitude of the force or the magnitude of the force when we're at the maximum position. For D, and this I also maybe would say is a general thing, most of the time, not all the time, but a lot of the time we can relate the maximum speed of the block, depending on what you're given, the maximum speed of the block for simple harmonic motion to the maximum amplitude using conservation of energy. So I know I talked about this in class, but I do think that this is kind of a slept-on tool that you have at your disposal, maybe I would say. We do have the relationship, and this one that's coming from just the formulas themselves, that the omega times xm is what's in front of our sign for our velocity. But that also comes from if we're at our maximum maximum spring potential energy, and we relate that to when we're at our maximum kinetic potential energy, that actually gives us that same relationship of omega times xm ends up giving you Vm. So that's just another, since we technically have mass, we have the spring constant, we have the amplitude, that would be something else that you could get to using conservation of energy to get to that Vm. But for the sake of time, I'm going to go ahead and use this shorter one. So I already forgot. This feels like a million years ago. I'm writing down the wrong omega. Our omega here was 8, and our xm was 0.2. So our Vm should be 1.6 meters per second. And then our last part of this question is to find the two positions at which the kinetic energy and potential energy of the system are equal to each other. So in general, we can say that our total energy is going to be split between kinetic energy and spring potential energy for this whole entire system. We can also say at least one point in time, the total energy will be all in the form of either potential energy or in the form of kinetic energy. So if we can find a value for the maximum spring potential energy or the maximum kinetic energy of our mass, that would give us our E total. We could use either. We know enough at this point in this problem that it's really just a matter of preference. Which one you would want to use, the 1/2 kx squared or the 1/2 mv squared. And then really the key thing that I think is a problem solving thing is just that we're looking for where US is equal to K. So, and we're looking at the X values where those take place. So something I would do for this is I'm essentially going to plug in a second US for this K, since I want to know when they're going to be equal to each other. And then I'm just going to set that whole thing equal to the maximum spring potential energy that we have. So I'm going to just get a number for that first. So 2 times 128 times 0.2 squared gives me 2.56 joules. And then if I divide that by 2, that gives me the value of just what the spring potential energy would be at that point. And then we could put in the more general equation for the spring potential energy when it's equal to that 1.28 joules. 1/2 times 128 x squared. That would basically lead us to, let's see here. X is going to be equal to, and again, there we're looking for 2. And let me clean this up actually a little bit. when we're taking the square root of a number, technically we have two values that are coming out of that solution, the positive root and the negative root. And if I actually go ahead and take the square root of that 0.02, x could be equal to either positive or negative 0.14 meters. It would give you back this same amount of energy. And then we can, I guess, could we check this? I guess in theory, I'm not going to, I think, spend time on this so that way we could do something else. But in theory, you could check this by finding what the velocity would be when the position is equal to this. That sounds like a ton of work to do. But in theory, you could do it and then calculate what 1/2 mv squared would be with that velocity and see if you get back 1.28 as well to match how the energy should be split. But again, that sounds like a ton of work. If you don't really have to do it, I probably wouldn't do it if I were you. Okay, but that was a very thorough, I think, review at least of the chapter 15 stuff. Almost the questions on the practice finals and the ones you've seen in your homework are all kind of pretty much like this, maybe with some slightly different things given and different things asked for, but this is a good sample. Yes?
Just in general, with the kinetic and potential energies be equal in like a spring mass system at half the amplitude?
It's not half the amplitude, it's a square root of 2 of the, I think it's 1 over square root of 2. If I do 0.2 divided by, yes. So yeah, so it wouldn't exactly be half the amplitude just because of that squared relationship in the energy, so that's why it's 1 over square root of 2 of the amplitude. But yeah, and then the velocity would also then at that point be 1 over square root of 2 of like the amplitude of the maximum velocity. Yes? Yeah, I mean, basically if I had set this up kind of generally, that comes out. I'll do it in a different color so we know that we're doing something separate here. But if I started from saying 2 times our potential energy at this point in x that we're looking for is equal to our maximum, then I could put in 1/2 k x squared, 1/2 k xm squared, and then the 1/2s and the k's go away. And I can get a relationship that's basically 2x squared is equal to the amplitude squared. So then my x value would be equal to my amplitude squared over 2. And then if I take the square root of both sides of that and simplify it, that would give you x plus or minus xm over the square root of 2. So yes, you can also get to it that way. But I know people have been complaining about me doing things symbolically. So that's why I also wanted to do some numbers here. And if you did the same thing with kinetic energies, basically you'd get that same Vm over square root of 2 would be equal to V. But yeah, what else do we want to see? Elizabeth?
Could you do number 3 on the other faculty?
Yep. So fall question 3. Okay. Yes. Reminiscent of something we've seen on one of our exams. Okay, so for this one, we have a 0.01 kilogram block. It's released from rest at point A. I don't know that I'll be able to do, this is maybe as nice as I'm going to be able to do. This is going to be our point A. Point B is going to be halfway up the ramp. That's our point C. We're calling this H. We do know the radius of this. I'm going to write it off to the side. And then this is actually also going to be, I guess I'll just do it like this. That's 0.5 meters, but B and C are at the same height. So R is also equal to 0.5 meters. Okay, so release a vertical distance H. I'll also just start plucking out my speed at A is 0, so I'm going to write VA is equal to 0. Slides down an incline track around a circular loop and then up another incline. The block slides off the track with a speed of 4 meters per second at point C. So I'll also tug that out, which is a height of 0.5 meters off the ground. Assume the entire track to be frictionless and air resistance is negligible, and our first thing we want to know is our height H. Okay, and then to me, at least first glance at A, is conservation of energy, because we've got some changing height and some changing speed, and our fastest way that we can connect those two as far as topics go is going to be our conservation of energy. So for part A, we want to know H. So I'm going to write out my E total at A is equal to my E total at C. I've got some gravitational potential energy at A, but I don't have any kinetic energy at A because my V at A is equal to 0. And then I've got some gravitational potential energy at C. If I'm calling the ground Y equals 0, which I don't see any reason not to at this point, so just kind of hoping that doesn't come back to bite me in the ass, but I think it will be okay. And then once I've got my energy accounting done of what types of energy I have at each of those points along the track, then I could put in mass times G times H is equal to mass times G, and I'll just put in that 0.5 plus 1/2 m VC squared. Just since I didn't have a variable that I used for that height at C, so I just plugged in the 0.5. But we can cancel out an m from everything. And then otherwise, I do just want my H by itself. So I could do that by dividing everything by G. And then start substituting things in. So my 9.8 times 0.5 plus 1/2 of 4 squared gives me like a 12.9. And then if I divide that by 9.8, I get H is 1.32 meters. If I round that to the second decimal place. Okay, so we've got one thing done. For part B, we want to draw and label all the forces acting on the block when it's at point B, which is 0.5 meter above the ground. So if I'm just drawing my free body diagram here, then I'm going to have force of gravity exactly at point B, which is like exactly horizontal to the origin of our circle, our circular loop that I didn't draw very circular on my picture, but on the picture provided is very circular. And then we should have our normal force pointing in towards the center of the circle. And for the next part of the question, or the next two parts of the question, now we're bringing in some uniform circular motion stuff and thinking about like that the normal force is what's going to be keeping this on the circular part of the track, this mass, as it goes around that part, and then getting some information about that. So kind of what's maybe an asshole thing to do in this question, is that in part C, so it's asking for you to find the magnitude of the velocity when it's at point B. You technically don't have to do any math because you've already found it. So since, and I should just take a screenshot of this stupid thing, but this at least is documented in my figure. But since B and C are happening at the same height and this track is frictionless, whatever speed we found for part C is also going to be the speed of the object at part B. So you can make an argument of basically that since like point B also at y equals 0.5 meters, so therefore the velocity would be equal to what the velocity was at C, or I guess we didn't solve for this, but it was given to us, which is just the 4 meters per second. But regardless, you don't have to actually do any math to get this answer. You could still set up your conservation of energy, set up the conservation of energy, say between A and B. I think that would be something that a lot of people would think to do, especially after just doing part A of this problem. But there are some hidden, I guess, kind of speed things that are in there. Because once we do have that speed, D is then asking for us to solve for the magnitude of the centripetal force exerted by the track on the block. So really they're just asking about the normal force. The normal force in this case is what we can say is our centripetal force. It's what's providing the centripetal acceleration, the force that's providing the centripetal acceleration. So in that regard, maybe if I'm starting really from first principles, the sum of all forces acting along that centripetal axis or that radial axis would be equal to mass times our centripetal acceleration. I'll put vector hats on these. Then we technically have, if we're using conventional positive and negative directions, our only force acting radially would be a negative normal force. And then technically our vector of our centripetal acceleration would be negative, because that should also be going in the negative x direction at that exact point that we're being asked about here, times whatever the magnitude. So negative sign times whatever the magnitude is of that centripetal acceleration. We can simplify that. So the negative signs on each side will go away. Our definition of AC is that it's v squared over r. And then we have all of those values. So then we could put in the 0.1 times 4 squared over 0.5. 0.1 times 16 divided by 0.5. And that gives me 3.2 newtons. Okay, questions on any of that stuff so far? Because otherwise we're going to switch gears and go back to work energy stuff for the last part of this question. Where now we're saying, okay, let's say we have another track that's the same exact configuration, but now it has friction. We know for this track, we actually have H is going to be equal to 2 meters. And now we want to know what the work done by friction is. If now we need to drop this from 2 meters in order to get it leaving point C at that same speed of 4 meters per second. So really the only thing I'm changing to my energy conservation of like the point energy at point A, setting that equal to the total energy at point B, is that now I want to include the energy at point A plus the work that's happening as I go from point A to point C will be equal to the total energy I have at point C. So whatever energy I'm starting with plus the work, that could be positive or negative, being done on the system will be equal to whatever energy I have at the very end. In this case, the work from A to C is just going to be that work from friction. So as I kind of start to substitute things in, I will just write that as work with an FR subscript, so that way I know it's the work from friction. And then otherwise this is going to look pretty much the same, which is why I skipped a little bit of steps of writing out just the potential and kinetic energies before subbing stuff in. But so we can isolate that guy. Now we couldn't cancel out any M's, since now we're trying to solve for what that work is going to be, but otherwise we do have everything we need to sub into this. So 0.1, 9.8, 0.5, 0.1, 4 squared, minus 0.1, 9.8 times 2. And then we'll see what we get. Gives me negative 0.67 joules. And since this is friction, something that's inherently trying to slow things down, I would expect the work from that to be negative, because it's taking energy out of our system that it had to start with. Very long. And that looks a lot like, I'm going to go ahead and guess that what we put on exam 2 was inspired by this one, just looking at it now. Yes?
Can you explain why you added work to the energy?
Yeah, or why I added it at all, or why I put it where I put it. Okay. Yeah, because there's kind of a few different ways that I feel like these conservation of energy equations can get set up. The way that I like to think about it, and maybe I'll kind of go back to the picture that we have, and is mostly from like a storytelling, like I'm thinking about the story that's being kind of told in terms of energy. So like I'm starting off with some energy here at point A, but as I go from my point A to point C, there's going to be work acting on my mass the whole time. That could be something positive. That could be work, say, in, I don't know, in a form of a jetpack. Let's just say that's going to have this thing speed up the whole time that it's going across this track, such that the energy at C is more than we had when we started at A. Or it could be like in this case where we have work happening that whole time from A to C, but it's friction, so it's slowing us down. It's taking energy out of our system that whole time. So really, that's kind of when I write then to go back to kind of what I have written down here, is I am thinking about, this is the energy I'm starting with. This is energy transfer. So work in general is just like our energy that's being transferred. So the energy I'm starting with plus whatever is being transferred is going to have to be equal to whatever I'm ending with. Does that make sense? So yeah, there's kind of a few different ways that textbooks and stuff will set this equation up with the E totals and the work, but this, at least from the story of how things are unfolding, I think kind of makes the most sense to me. Yes?
Does that mean you could put it on the right side?
Yep, so the other way that I've seen this is instead of having your work from A to C on the positive side, you have your work from A to C on the right side, but then it's a negative. And then I think the way that we kind of have it written in your book is then even, or not in your book, on the equation sheet, is that you have the work from A to C is basically equal to the change in that total energy, where that change in total energy would be your E total at C minus your E total at A. So that would be even a third way. That technically it's on that equation sheet, but maybe not super explicit. What else you got for me? This was a nice force energy review, centripetal motion review. Yes.
On the other parts of the exam.
Yes.
Spring one.
Back to spring.
Question 7.
Question 7. Okay. Yeah, because we did talk about, this will be similar to our simple harmonic oscillator, but it will be a little different. So, spring, practice final, question 7. So for this one, we have the displacement of a transverse wave on a string is represented by the following equation. So we have y1 as a function of x and t is equal to 4.2 sine of 0.8x minus 47t. And then they're telling us that y1 and x are in centimeters and that t is in seconds. So we can have some of that context as well. Then our first question on this is, what is the speed of a wave on this string? And based on kind of what I can pull out to start, I can pull out the amplitude. So my ym value would be that 4.2. That should be in centimeters since it's saying that my whole function for y1 is in centimeters. I could pull out that my k, my wave number, is going to be 0.8 radians per centimeter. So that's also just something I'm maybe not going to convert, but to be aware of when I'm reporting units. And then if my t is in seconds, then my omega is going to be 47 radians per second. So for my wave speed, I can start off by using one of the many definitions of wave speed we have, but since we have omega and k, I'm going to go ahead and use the one that has omega and k in it. And then maybe just keeping in mind for myself that the 0.8 is in centimeters. So when I do take the 47 divided by 0.8, that's going to give me a speed that's in centimeters per second. But since this is not specifying that I have to report it in meters per second, I'm just going to leave it in the centimeters per second for now. Second part of this question is, what is the speed of a particle on the string when x is equal to 3.2 centimeters and t is equal to 2.5 centimeters? So this is getting at the difference between the wave speed and then the speed of a particle at any given time. So this omega over k, lambda over period, this v is always going to be our wave speed, but for our particle speed, that's actually going to be governed by that first time derivative of that y1 function that they gave us to start with. So if I take the time derivative of, I already forgot the function, I guess it's right in front of me, of 4.2 sine 0.8x minus 47t. I guess I'll call that v1 as a function of x and t. And I should get a negative 47 will come out of that. So we'll do some little, that part will stay the same. So we've changed our sign, pardon me, we've changed our sign into a cosine since that had a time inside of it. And then by chain rule, we have to multiply by the time derivative of that negative 47t, which just gives us an extra negative 47. So I can simplify this. As negative 197 times cosine of all this stuff. And then I have to just plug in the time and the position that we're given. So then, negative 197 times cosine of 0.8 times 3.2 minus 47 times 2.5, and that's all in radians, so that's all good. 0.8 times 3.2 minus 47 times 2.5, and that gives me a V1 of 53, and then this would also be centimeters per second. Keeping that consistent. But why? Did I do that multiplication wrong? No. Maybe they wrote that down in the solution. I'm gonna ask a stupid question. It's embarrassing. I feel like I'm just looking at the solution, and I'm off by a negative sign. Is the derivative of sine negative cosine? I thought sine was positive cosine and cosine was negative sine. Yeah, if you don't mind fact checking that for me. If not, then I'm confident that this solution missed a negative sign somewhere. Okay, then I'm right, the solutions are wrong. Because otherwise I don't know how you would get, yeah, they're off by a negative sign compared to what I have written out, so not sure what happened there, but they have written, yeah. But they also got 53, so at least that part we can check ourselves on. Okay, and then the third part of this question, write an equation that represents a second wave which when added to the transverse wave described above will create a standing wave. So that, well, I guess that's not something that we...
So nothing with standing wave is on the
Yeah, I'm like, that's not something that we went over in class. So now I'm actually forgetting what you need to do for... I think it's just that wave, but out of phase by a certain amount. But yeah, I'd say 3, 4, and 5, we don't have to... Well, is it just something more general? Oh no, okay, that is something specific. Okay, yeah, so I'd say you can ignore 3, 4, and 5, parts 3, 4, and 5 of this question. That won't be relevant for your exam. What else do we want to see? Yes.
I'll go to the back of Walmart. I have a problem at 7 for angular
That omega t is 1. So I could see in a case where you have constant angular acceleration and the initial angular velocity is 0, that your change in position would be equal to that. Like, because I'm thinking about like the theta, like part of that sounds like this equation to me.
Yeah.
Do you happen to have like a screenshot or something of the problem that they gave you?
I wrote down most of the information.
Okay.
They gave you the radius. It was a wheel that was turning. They gave you the radius of the wheel, and then it said it had a cord wrapped around the wheel.
Okay.
And it gave you the angular acceleration.
And they specified that it was constant.
I guess so.
Okay.
Then in the solution, it was like that was constant and stuff. Yeah.
And was it asking for like the amount of turns that it went through?
So it said that it had a 4-meter cord wrapped around it, and it asked how long it took the cord to unwind when the wheel was spinning at that angular acceleration.
Okay. Yeah. So you could relate. Gotcha. Yeah. So basically, like that 4 meters, 4s. Okay. The 4 meters that they're giving you, I would say that would be like a change in angular, like the arc length is how much is unwinding. So then 4 meters divided by whatever the radius is, that would give you your change in angular position. And then if you knew alpha, and I guess they would have had to specify that it was like starting from rest or something, because that would be the only other way. Like if you got your omega 0 equal to 0, then you could basically get something from this equation that the shorthand is that your change in theta would just be equal to 1/2 alpha t squared. But yeah, recognizing that the 4 meters wrapped around, you can then get that to a change in radians. Maybe also wouldn't be obvious. How'd you like the adaptive review otherwise? No? Not okay.
Some of the questions are just kind of janky.
There's kind of what? Janky?
It's like,
Okay.
There was a question about like if you step on the pedal of a car, like what's providing the force for acceleration?
Oh,
Yeah. And, like,
okay.
some of them are fine.
That's what I was a little afraid of. Yeah, things like that. Then it like being like completely derailing the rest of everything because you got something stupid.
Yeah.
But hopefully on average it's helpful. Yeah.
I was gonna ask, do you think it's a good use of time? Like, what would you recommend doing?
I wouldn't say, like, if it actually worked the way that it is supposed to work, I think it would be not a bad use of time. Just because it's mixing everything all at once. So it really can give you, like, a sampling across the entire semester's worth of material of, like, just giving you problems. But we can kind of achieve that ourselves also, just like, which, and probably most of you don't do this, but like I have screenshots of like your homeworks that like I put into Google Docs, like just for myself to then be able to print out because I like to have a physical copy. But like in theory, you could make up your own like fake exam by pulling like one question from each homework and maybe putting it together and like randomizing it, and even just going through and can you recognize, oh, this is coming from this chapter of material, this is how I would solve it. Like I think some of that as far as like efficiency of like being able to recognize what you would use to solve it is kind of the most valuable thing. And I think a lot of you have seen that on the grading so far as well, that it's like if you can at least recognize, all right, this is what I needed to do to solve it, but you don't get the chance to actually execute that, that goes a lot further than let me just randomly find an equation and see what I can jam in here. So I think more of the triage kind of practice you can get, I think the better. Because like, yeah, I don't remember now if we have the exam itself structured in a way where it's like, I don't think we're starting from the earliest material and going to the latest material. I think we start with the new stuff and then get into the older stuff. But that's just like another factor of like things to consider of like how things are going to be mixed up. How might that affect your timing of doing problems? But I do think using, and I've given this advice to some people, of like using the practice exam, at least one of them, as like a self-check for yourself, which is kind of what I like about the adaptive review also, is that if you do a self-test on one of the practice exams and you're like, okay, feel confident on, say, a collision, or I feel confident on the new material, but I still don't really know what's going on with fluids. Let me do maybe 3 practice questions each on the stuff I'm comfortable with, but I'm going to give myself like 10 questions or just more dedicated study time to what you need more practice on. So that's what the adaptive review is also supposed to do for you. But there's some kinks to be worked out. All right, and if we're feeling like there's not a ton of other questions, I might just call it early. I put it from 2 to 4 just in case. But at least y'all don't seem like you're chomping at the bit, but you can correct me if I'm wrong and there's stuff you really want to see. All right, then otherwise, so tomorrow, I put this in the announcement on Canvas, but tomorrow we'll have the regular drop-in study session type vibe over at Remick Family Hall. 15 minutes before that starts, I'm going to have my dog. So my plan is to get him walked, drop him off at home, and then I'll be at the study sessions actually working the study session the second half. So I think from like 5:30 to 8, I'll be there actually working, but Professor Yates said that she should be there basically the whole time, and there's engineering physics tutors that'll be walking around too, that they'll be able to help you. We might not be able to help them, but they'll at least be able to help you for sure. Be like, oh, I remember when I was in